Hello. So today we are going to be talking about the concept of Nyquist Stability Criterion. In control systems, we have a particular interest to find the stability of a system always. Previously, we used to use Ruth-Hurwitz criterion to figure out the stability of a system. But then the characteristic equation at sometimes gets complicated, honestly to say. So since it gets complicated at times, you need to have an ulterior method to find out the stability, for which we use the Nyquist stability criterion. So basically, Nyquist is a graphical way of figuring it out instead of going it the traditional algebraic route that the Ruth-Hurwitz criterion basically takes. So the Nyquist criterion helps us to determine the closed loop system's stability using the open loop, which is a interesting thing to note at this point. To understand much more of it, we need to understand the graphical part of the system. This Nyquist stability criterion is not only reliant as just as a formula, which is where a lot of people make a mistake. They just remember the formula, so they will have no idea how to implement it in a question. So, anytime you learn Nyquist stability criterion, synonymously you need to learn Nyquist plot. So, a Nyquist plot is where the open loop transfer function is taken, and the points in the open loop transfer function are plotted on the S-plane. Now, let us understand a very important point where stability of any system is dependent on the number of poles or zeros that lie on the right half of the plane. I'll repeat, the stability is determined by the number of poles or zeros that are in the right of the plane. So that is why we create an extensive Nyquist contour, basically another graphical representation in the S-plane, where we completely cover the S-plane, right half of the S-plane, keeping the radius of this Nyquist contour to infinity almost. We map the points that are in the S-plane, right of the S-plane. The Nyquist contour is basically plotted onto the omega plane, where the Nyquist plot exists. So this Nyquist plot is something that we need to have to even implement the Nyquist stability criterion. Now, to make things much more clearer for you, let us just jump straight into Nyquist stability criterion, where the formula is very simple. We have seen it everywhere. N is equal to P minus Z. In many other textbooks, you can also see a notation of Z minus P, which is not wrong. But I would recommend you to just stick to one notation, because even in this N is equal to P minus Z, we have two other way of looking at it. So let us just not confuse ourselves and just stick to one thing. So N equal to P minus Z is the notation I'm taking here, where N will be the number of encirclements around the -1 point. Now, you in the Z explained, so clearly you know that. You might be thinking like, why are we using -1? I mean, like, shouldn't we always encircle the origin in most of the cases? Which I agree as well. Uh, but I would like to explain to you how it works. So the anti-clockwise direction is taken as positive and the clockwise direction is taken as negative. The other points being P is the open loop poles in the right half of the plane and Z is the closed loop poles in the right of the plane. In this notation, please don't get yourself confused and be thinking, oh, Z means you have to take it as 0. Again, I'm repeating, P is the open loop pole in right of the plane and Z is the closed loop pole in the right of the plane. So this criteria, this part of the notation is very much aligned with finding out the closed loop stability. And usually this formula you should take when you have information about the closed loop systems, poles and zeros. Okay, well, again, I'm repeating. You take this notation if in the question there is information about the poles and zeros of the closed loop system. Okay. Now, most of the times you will not have information about those things, which is very understandable. So I think we have to move to the next part of the which is the open loop notation. So in the closed loop notation, you saw why we were using -1 plus J0 is because usually in open loop system, the characteristic equation looks as G of S, H of S equal to 0. But in closed loop system, the characteristic equation looks like 1 plus g of s h of s is equal to 0. So there itself you can see why minus 1 is taken as the origin here. Basically, we're shifting the origin to make us not get more confused. Just stick to a notation where g of s, h of s is going to be the notation, but if it's equal to 0, we have an open loop system stability that we are considering. If the origin is taken as minus 1, then we're considering the stability for a closed loop system. Very easy. Now, the second notation that we are going to be looking into here is basically n equal to p minus z, the same thing exists, but here the n means number of encirclements around the origin. There it was around minus 1, here it's around origin. And p is the number of open loop poles in the right half of the plane, and z is the open loop zeros in the right half of the plane. So, which is all clear with the amount of notations that we are looking into. This second notation you use only when you have information about the open loop poles and zeros. When you don't have the information about the closed loop and anything, and you have open loop poles, or the graph itself looks very like aligned to the encirclements in the origin. So then you use this notation. So I would recommend you to remember both of these notations, because usually they just stick to one notation, and when questions come up, you tend to stumble because you are just like, oh, there is nothing around the origin. So I recommend you, based on the questioning, you need to be flexible with your thought process as well. Next, we need to understand the most important point of the Nyquist Stability Criterion, which is to how are we going to analyze the stability? Because in most of the questions, they will ask you what are the number of closed loop pools, open loop pools, and what is the open loop system stable or closed loop system stable. So for stability, the open loop stability, you can only understand when P is equal to 0. And for closed loop stability, when Z is equal to 0 for the first notation. Like you have seen this notation where you have clearly seen where the Z basically means what? The number of closed loop poles. So closed loop poles determine the stability for a closed loop system. So that is why a simple understanding of the Z is equal to 0 for the first notation means the closed loop poles are not there at the right hand of the plane. Also note that these poles that I'm constantly talking about, they need to be within the Nyquist contour when we plot itself. They shouldn't be something that you figure out at this point. The poles should be inside the Nyquist contour itself. If they're outside the bounds of the Nyquist contour, then basically they are something that you should be considering. So a simple summary of all this information that I would, the main thing that I would want you to remember is that an Nyquist stability criterion is a simple formula of n equal to p minus z, which is always associated with the Nyquist plot. So based on the arrangement of the Nyquist plots, or based on the design of the Nyquist plot, we will easily derive the information, and we will be able to understand two things. We will get two things out of this. First, we may get the stability of the system. And another thing, information that we may get is that if the n value is known and if the p value is known, we might be able to find the number of closed loop poles, or we might be able to find the number of open loop zeros. All of these things, information, mix and match, plug and play, we'll get it. That is it about the Nyquist Stability Criterion. I hope you understand this session very clearly. Thank you for the time. Thank you. And in the next session, we will continue to learn more things about the next coming up concepts. Thank you.